Welcome back to Applied Mathematics. In this video, I want to talk about area formulas, area units, and other concepts related to the area of a figure. You should at least be somewhat familiar with the idea of area as a way of describing the region enclosed within a two-dimensional object. The typical introduction to area starts by talking about a rectangle. If we have the length and the width of the rectangle known, then the area of the rectangle is given as the length times the width. And if we think about the units going on here, let's say that our length is 7.5 feet and our width is 3.7 feet, then the area is going to be the product of 7.5 feet times 3.7 feet, which my calculator is happy to fall on the floor and not actually do calculations. My calculator is happy to tell me that that's 27.75, but rounding that to two significant digits, I'll write it as 28. And then in my units, I am multiplying feet times feet. And feet times feet is the definition of feet squared. Because the US customary system has an absolute aversion to anything that looks like mathematical notation unless it's a fraction, very often, instead of feet squared written like this, you'll see it abbreviated SQFT. Those two sets of units are completely identical, and it's just a matter of notational convenience which one you're going to use. I guess naturally that leads to the question of what is a square foot? And in a very circular sort of logic, well, a square foot is a square, which measures 1 foot by 1 foot. And the typical discussion here talks about using this as a tile, placing tiles down across your region, and using that as your denotion of area. But if we're going to talk about area units in square feet, we should also be able to talk about square inches, square yards, square miles, square meters, and so on. And if we can talk about measuring things in various different units, we should be able to convert between them just as easily. So as an example, let's take 2.5 square feet and convert that into square inches. In order to make sense of this, I'm going to go with the exponent notation. Instead of writing it as SQFT, I'm going to write it as feet to the second power. And that second power is going to make this whole process make sense. Because sure, we know that there are 12 inches in 1 foot, and doing that would cancel out a factor of feet. But there's not one factor of feet, there's 2 factors of feet in square feet. So in order to get from square feet to square inches, I need to multiply by that factor of 12 inches over 1 foot, not once, but twice. Because 2 factors of feet down here will cancel out the 2 factors of feet that are the definition of square feet. Then we will get inches times inches, and inches times inches will likewise be the definition of square inches. All right, so I've got 2.5 times 12 times 12, which my calculator tells me is 360. And the algebraic notation would be inches to the second power, but we can just as easily write that as SQIN. All right. And so whenever you're dealing with area units, whether it's square feet or square inches, square yards, square centimeters, square meters, and so on, you have to remember that there are two factors. Those come out of how you use the formula to calculate the unit in the first place. If there are two factors, you need to multiply by the conversion factor twice. There are 12 inches in 1 foot. So there are 12 by 12. Right? If I have my square foot here, and I divide it up into square inches, I get 12 marks going across and going up and down. There are 144 square inches in a square foot. Moving on, while we're talking about area units, I guess area formulas was what I said we were going to be talking about. And so let's just go through a couple of different types of shapes. I wrote triangle first, but I forgot that I wanted to do rectangle first. We've already talked about the formula for a rectangle. The area of a rectangle is the length times the width, where the length is one of the sides, the width is the other. Remember that a rectangle is the shape that has 4 right angles. And the nice thing about having 4 right angles is that opposite sides have the same measure. So if the right side has length W, the left side will also be W. If the bottom is L, the top will also be L. Triangles can be a little bit tricky, and really this is going to apply to all of the other shapes that we look at here. But the issue with most shapes that are not rectangles is that one of the measurements you need is not actually a side of the figure, it's something else. All right, but we're going to choose one of the sides and we're going to call it the base of the figure, indicated with a B. We are then going to draw a perpendicular line from the base of the figure to the far point, and we're going to go ahead and call that distance the height h. And a triangle is half of a rectangle. I mean that very literally. If you take a triangle and you cut it along that altitude, the height that we just drew, and then you flip the pieces upside down, they will fit perfectly in order to give you a rectangle with the length being the base and the height being the width being the height. One of the things that tends to really throw students off working with triangles and some of the other shapes we're going to be dealing with as well is that sometimes the base and the height don't really feel like they line up. So the base is still the width of the figure that falls within the triangle, and then we have to extend the line of the base out so that it can meet the line coming down from the point at a right angle. It is still the same formula. There is nothing weird about this. It just looks like it shouldn't work, even though it works perfectly fine. And the same thing can happen with the other shapes that I wanted to talk about. A parallelogram is a shape that has two parallel sides and we're going to use the same vocabulary we used for a triangle. We're going to call this the base. We're going to measure perpendicularly and call this the height. And again, the important thing about a parallelogram, to recognize that it is a parallelogram, is that if we call the bottom length base, the top length has to also be base. And if we call this side length S for the side, the other side has to be that as well. We don't need to know those values in order to calculate the area of the parallelogram. That's why I wrote them in a different color. But it is important to have some indication that the thing you're dealing with is a parallelogram. Having opposite sides with equal length is a nice way of denoting a parallelogram. Having opposite sides that are parallel is also a nice way of denoting a parallelogram. But the area of a parallelogram is just the base times the height. Visually, I've seen this work out. If you take a parallelogram and you just cut this triangle out of it and move it over onto the other side, it does in fact form a rectangle where the bottom is going to be a length base and the top, or the width, is going to be of length the height. So yeah, it's basically the same formula, which is a little bit strange, but we are happy to have that. All right, I also want to talk about the trapezoid. The trapezoid is the shape that has parallel sides in one pair, and then the other pair does kind of whatever. And so we have these two parallel sides which have different lengths. And then we're going to need to measure the height between them. This formula messed with me for a long time before I finally realized that what we're really doing here, we're going to take the two bases, we're going to add them together and divide by 2. That is the average length between the two sides of the parallelogram, between the top and the bottom. So what I want you to think about is take your parallelogram that has these weird sides and then kind of just average it out so that they have the same length. In order to do that, you're going to have to take, part of this triangle and flip it up like that. You're going to have to take part of this triangle and flip it up like that, and then you'll have something that ends up as a rectangle. That's not the button I wanted. That's the button I wanted. All right, so take that average of the two base sides, multiply it by the height, and you will get the area of the trapezoid. All right, this picture of a trapezoid is very common, where the top is narrow and it flares out in both directions to give you the bottom. There is nothing about the definition of a trapezoid that says that that has to happen. This is also a trapezoid. Both of the sides seem to be leaning to the left, but one side is leaning more than the other side, so it is not a parallelogram. It is still a trapezoid. This shape is also a trapezoid. I might even have some right angles on it. In fact, this is a really nice trapezoid. It's kind of on its side. So the two bases are the left and right instead of the top and bottom. And then the side that is currently on the bottom is the height of the trapezoid, but it is still a trapezoid, and that's the thing that matters. And then the last shape that I want to work with here is the circle. We've dealt with circles previously. A circle is defined by some point called the center, and all the other points some equal distance called the radius away from that center. And the area of a circle is the constant pi times the radius squared. Most of the time, when you are working with an area formula, you're going to have taken some measurements of the figure, and you're going to be working through to try to find the area. For the sake of making the best value of our time, instead of using that approach for the example I want to do here, I'm actually going to do the opposite. So the approach I'm looking at is a little bit rarer. It comes up less often. It's a little bit more challenging. And because of that, I think it makes a good example for this video. Consider a trapezoid with bases measuring 7.50 meters and 4.25 meters. What height must this trapezoid have so that the area is 22.2 square meters? So what we're saying here is that we have the top and bottom established, and we're going to connect the top and bottom. We just don't know how far apart they are going to be. Right, the formula for a trapezoid is fairly straightforward. We've got an area, 22.2 square meters. We've got two bases. It doesn't actually matter which one is which, but one of them is going to be B1 and the other one is going to be B2. We've got a height that is unknown. And we're trying to solve for h. As I've talked about in previous videos, you could plug all of your numbers in and go through and solve the equation from there. There is technically nothing wrong with that, but I encourage you, and I want to take the time to go through and rearrange the formula first, because I think that that is good practice, and for applications that are a little bit beyond the scope of what we have time for in this course, those sorts of things are important. Right? Chances are, if you're looking at solving a problem like this, it's not a one-off problem. Chances are you have a whole bunch of different bases, you have a whole bunch of different areas, and you're trying to figure out how to set up the heights for each different one. And so you're going to be using this formula quite a bit. All right. The first thing I'm going to do here is multiply both sides of the equation by 2, because I don't want to deal with a fraction. And then to get h by itself, h is currently being multiplied by b1 plus b2. So divide both sides of the equation by b1 plus b2. Now we have our formula solved for h. I didn't quite leave myself enough space to actually do anything with it. I guess I should switch the order. We usually have the thing we're looking for on the left-hand side, but I can fill in all of my data. I can grab my calculator. I can be very careful punching this into my calculator. And my calculator tells me that h should come out as 3.78 meters. All right. And the units here do make sense. Two ways of thinking about the units. First of all, if my base lengths are in meters and my area is in square meters, then sure, my height should be in meters as well. That makes sense. Another way of thinking about it, well, I've got square meters in the numerator. When I add meters and meters, I'll have meters. If I have square meters and I divide by meters, I will be left with meters. It always works out nicely like that, so we can use that to our advantage. All right, that's just one example of playing around with these formulas. I don't really think that there's too much else I need to talk about here. So take some time, practice using these formulas, calculating areas of various different shapes, and I'll see you in the next video.